So today I will be discussing on this particular topic, that is determination of half-life, volume of distribution and clearance. So let's know what is half-life. Half-life is basically a time period. So it is basically a time during which the drug concentration reduces to half of its original one. Means initially the concentration, whatever the concentration is there in the blood, that concentration gets reduced to half of that. Then that much time in which this occurs, that time period is known as the half-life. So mathematically, half-life has different formulas for different kinetics. If I'll talk about first order kinetics, then it is having a different formula, and in case of zero order and second order kinetics, it is having a different formula. But today I'm going to talk on the half-life if a process follows first order kinetics. Now let's see what will be the formula. So here the formula is this one: half-life is equal to 0.693 upon K. Now half-life is usually represented by this symbol, that is known as T, half. And what is this K? K is known as elimination rate constant. And how we have obtained this formula, let's discuss that. To get this formula, you need to have first order equation. If you remember, one CBM IV bolus equation was C is equal to, C was there and it was equal to, C naught e raised to the power minus kt. That is usually a equation, mono exponential equation, which we have obtained in case of 1 CBM IV bolus, and I'm going to use this equation to calculate the half-life. So what usually happens, what is this C? This C is the concentration of the drug in the blood, and this C depends on the time, this time. So if time is 2 hours, and if you solve this equation, then whatever the C you'll get, that C is the concentration of the drug at 2 hours. And if you change this time, if you put time equals to 4 hours, and after solving this, then you'll get a concentration of the drug in the plasma at 4 hours. So it means this C is directly related to the T. Now to calculate the half-life, what we need to do? So as per the definition, we know that at T half means at half-life. At half-life, there is a particular situation. What is that situation? Half-life is the time at which the concentration of the drug in the plasma reduces to half of its original one. So C naught is the original concentration and the C is the concentration at this time period. So what we can do, we can put C equals to C naught by 2 at T half. Now we are going to substitute the values or put the values in the above equation. So if we'll put the values in the above equation, then our equation will become like this: C is equal, C, instead of C I'm going to write here C naught by 2, because I have said that C is equal to C naught by 2 as at T half. Then this C naught by 2 is equal to C naught e raised to the power minus k, and then it is T and it is half, right? Now this is a mono-exponential equation. To convert into a straight line relationship, what we need to do? We need to take the logarithm on both sides. So we can take the log here, and this equation will be converted into this. Log of C0 by 2 is equal to log of what you can say C0, and next will be minus kt half. Now t half is the time point which we have specified. It is not it is a particular time point. That's why we have defined it. And in the subscript, in the denominator, I'm going to use a factor that is 2.303 because I have taken the 10 base logarithm. So now shift the terms. After rearranging the terms on both sides, what we'll get? We get kt half is equal kt half upon 2.303. That has come because I have shifted this part here towards this side, so negative sign is negative will become positive if you are going to shift it, and this side it will become log C0 minus log C0 by 2. So after rearranging, we'll get this type of equation. And we know if we are having log A minus log B, then we can write this as log A upon B. So similarly, I'm going to use this formula here, and I can represent this by this thing, log C0 upon C0 by 2. Now C0 and C0 is common in both denominator and numerator, so it will get cancelled out, and since 2 is in the denominator, it will come up, and equation will become like this. Log 2 will be there in this side. So what I'm going to do here, I'm going to keep t half on this side, and rest of the term will be shifted to the other side. And when I'll shift rest of the term, then this log 2 will be multiplied by this factor, that is 2.303, and in the denominator what we'll get? We'll get the k. What is k? Ka is the elimination rate constant, and if you see the value of log 2 from the log table, put that value here, multiply it with 2.303, then you'll get 0.693, and in the denominator there is k. So finally we have obtained this formula which says that t half is equal to 0.693 over k. Now here what we know, that elimination half-life can also, this is one of the formula to calculate the elimination half-life, but elimination half-life can also be calculated from the graph also. Means if we are having a graph, then we can calculate it very easily. Now I'm talking about a particular graph, a graph of 1 CBM IV bolus, a semi-logarithmic graph especially. So in 1 CBM IV bolus, we know that whenever we are going to take logarithm of C on the y-axis and time on the x-axis, then usually we get a straight line, a descending straight line, and slope of this straight line is equal to minus k upon 2.303, and intercept of this straight line, means if you will extrapolate this straight line towards y-axis, so at the point where it is going to meet the y-axis, that point is called C0. So intercept of this point is called log C0. So it means from the graph you can calculate the value of C naught right here. And we know that T half is that time at which the initial C naught reduces to half. So if this initial C naught is having a value of 50, right? So this is the point at which its value is half of the C naught. So what you need to do, you need to just draw a line parallel to the x-axis, and where it cuts this descending straight line, then from that point drag it downwards towards the x-axis, and the point where it is going to meet at the x-axis, this point is known as the half-life of the drug, or you can say T half. So it is very clear now that from the graph also we can easily calculate the T half. Now one more formula is there to calculate the T half, and this formula is based on the values of apparent volume of distribution and the clearance. Now I'm going to discuss this formula later on, because to understand this formula you need to know what is volume of distribution and what is clearance. So let's talk about the volume of distribution. Now this is the apparent volume of distribution. So basically the volume of distribution is the volume of the fluids which is there in our body. So it is the total volume of the fluids into which our drug is getting distributed, or you can say dispersed, and VD is equal to the amount of the drug in the body divided by the plasma drug concentration. Now this has been derived because we know that there is a direct relationship between the amount of the drug in the body and the concentration. We know that amount of the drug in the body is directly proportional to the concentration of the drug in the plasma, right? And whenever we are going to remove the proportionality sign, we need to add a constant. So here we are going to add one constant, that is called VD, and VD is called apparent volume of distribution. So VD will become, after rearranging this equation, we'll get that VD is equal to X over C. So finally we have arrived to the same equation. VD is equal to X over C. Now X, in case of IV bolus, X, this X naught is representing the dose of the drug which we have administered. Say if I have administered tablet which is containing 500 mg of paracetamol, then this 500 mg is the dose of the drug, and C naught is the initial drug concentration, means after administering the drug, whatever the concentration is there in the blood, that is called initial drug concentration or original drug concentration. Now this C naught can be easily find out in case of 1 CBM IV bolus. How can we find out? We have to plot a graph between log C versus time, and we know that this graph is a straight line, and if we extrapolate this graph towards the y-axis, then this point where it is going to meet the y-axis, this point is known as log C naught. To calculate the C naught, you have to take the anti-logarithm of this, and finally you'll get to know the C naught. So this equation is useful in case of 1 CBM IV bolus, but in case of 1 CBM extravascular, we cannot use this equation to calculate the volume of distribution. We have to use another equation, and that equation is this. This is called model independent equation. Means this equation is not based on any model. So that's why we can use this equation. Here VD is equal to Fx naught over Ke AUC. What is F? F is fraction bioavailable. If F is equal to 1, that it means whole amount of the drug which we have administered that has been absorbed, and if F is equal to 0.8, it means only 80% of the amount of the drug has been absorbed in our body. So this is the significance of F. And why we have added F? Because we know that in extravascular system there are less chances that complete absorption of the drug never takes place because of so many factors. We have studied all those factors under the biopharmaceutical part, because physicochemical properties of the drug, then physiological factors, and sometimes the pharmaceutical factors are going to reduce the entry of the drug into the blood. So due to all these factors, 100% of the absorption never takes place in the extravascular case.